So let's talk about resonance, which is a very important topic, especially for those of you who plan to move on to organic chemistry. You'll find that resonance, this idea, is very important in terms of explaining and predicting certain properties of organic molecules. So, what is this resonance all about? Well, if you draw enough Lewis structures for different molecules and ions, what you're going to find is that it's possible to represent a particular molecular structure with two or more plausible Lewis structures, and the only difference between them would be how the electrons are distributed. So if you look at the example of ozone, what you see here is the ozone molecule, the Lewis structure of the ozone molecule. And here is another representation of the same molecule. And if you look at these two and compare them, you'll see that the difference between them would be how the charges are distributed, right? So for example, here you have a -1 charge on the oxygen on the left, but over here the -1 charge is on the oxygen on the right. But not only that, you'll see also that there's a difference in terms of how the electrons are distributed. So let me turn on my pen here. So you'll notice, for example, that in this structure here, you have 6 electrons on the outer shell of the oxygen here and a single bond here, right? But in this structure here, you have 4 electrons on the outer shell of this oxygen and a double bond here. And you have kind of like the reverse occurring as far as the other end here. You have a double bond here with 2 pairs of electrons, lone pairs. But here you have a single bond in the same location, and you have 3 lone pairs. All right, so there's a difference between these two, and therefore one can in fact generate one from the other by pushing this pair of electrons here, which would mean that this pair of electrons will be forced out here because the oxygen here cannot have more than 8 electrons. So therefore, as a result of that movement of electrons, you end up with the second structure over here. All right. Now, the reason why resonance was a theory that was developed was because it was discovered that there's some discrepancy between what the Lewis structure suggests about the ozone, let's say the ozone molecule, and what was actually found experimentally. Let me try to explain what I'm talking about here. Now, if you go by this structure, for example, right, you would expect that the length of the oxygen-oxygen bond here would be longer compared to the length of the oxygen-oxygen double bond here. And we're going to see later on that one would expect that because, typically speaking, single bonds will be longer compared to double bonds, which will be longer compared to triple bonds, right? The more bonds you have, the greater the attractive force between the atoms, and therefore the shorter the bond. So you'd expect that this bond here would be longer in length compared to this bond here, right? What was actually discovered, of course, using instrumentation and so on, what was discovered was that these two bond lengths are actually the same. And not only that, it was discovered that the bond length here and the bond length here, which are the same, is about somewhere in between that you'd expect for a typical single bond and a typical double bond between two oxygen atoms. So therefore, it's for that reason why the resonance idea, theory, if you will, was developed. So basically, what the resonance theory says is that, and I'm going to use ozone to explain it here. What the resonance theory says is that this molecule or this structure does not in and of themselves represent the true structure of the molecule, but that the real structure of the molecule is a hybrid between those two structures, right? And that hybrid is called a resonance hybrid. All right. So basically, what this theory is saying is that you can't expect the real molecule to look like this. You can't expect it to look like this either. But the real molecule of ozone is somewhere in between. All right, between those two separate resonance structures. And the analogy I like to use to explain this further from biology, we know that a donkey, well, I should say a mule, is the hybrid between a donkey and a horse, all right? So what that means basically is that the mule has some characteristics in common with a horse and other characteristics in common with a donkey. So that's the same idea that is used to explain the real structure in relation to the Lewis structures for, or the resonance structures for, in this case, ozone. And this applies to other molecules as well. Now, the electrons that are part of the resonance hybrid are basically said to be delocalized. So basically what they're saying is that this pair of electrons here, right, which, or I should say this pair of electrons here, which comes here, and this pair of electron moves out here, basically do not belong to this oxygen or this oxygen, but is basically spread out from this oxygen to this oxygen, right? So we say that the electrons are delocalized. And that's a very important idea to keep in mind. As I said before, when you get to organic chemistry, this whole concept of delocalization and resonance structure, they're related and can be used to explain certain properties that organic molecules will display. So let me use the example here of the carbonate ion so that you can see how we develop the resonance structure. So let me go to my pen function here. And let me just start off by drawing the Lewis structure of the carbonate ion, which we did before. If you recall, the Lewis structure of the carbonate ion is CO, double bond O, single bond O, and you have a negative charge here, a negative charge here, right? So one resonance structure can be generated by pushing this pair of electrons down here, right? Which means that this pair of electrons will have to move out to this oxygen here because the carbon cannot have more than 8 electrons on its outer shell. So therefore, the resonance structure generated as a result of that would be this. Single bond C, O minus, and then a double bond here, O. So that's one resonance structure. And then the third resonance structure can be generated by pushing this pair of electrons here, and this pair of electrons will go here, and you'll end up with O, double bond C, single bond O, minus, single bond O, minus charge here. All right, so those are the three resonance structures of the carbonate ion. And I should add some other symbols that you'll that are used typically when it comes to resonance structures. So you'll notice I use a double-headed arrow here. That basically indicates that the relationship between the structures on either side is a resonance relationship. It doesn't mean that a reaction is taking place. It doesn't mean it's a reversible reaction. It's basically telling you that the relationship between this structure and this structure is a resonance relationship. Another thing I should say is that typically, when it comes to resonance structures, we typically put them collectively within square parentheses as shown here. Okay, where's that thing? Okay. Okay, there's something going on here. I'm not sure what's going on. Oops. Anyway, so basically, we put the structures within square parentheses like that. All right. So that's basically how that is done. All right. So I'm going to stop this video here, and then the next video I'm going to start discussing bond order and bond lengths. All right. Until next time.